and welcome to the University of St Andrews. I'd like to extend a warm greeting to all of our alumni, students, colleagues and friends who are watching from across the globe. My name's Craig Rutherford and I work in the Development and Alumni team. This is if this is your first Saints Talk, then thanks for joining us. Our Saints Talks are short presentations by leading members of our academic community on key areas of our world-leading research. It's a little flavour of the expertise that our lucky students get to see on a daily basis. This evening's talk will be given by Dr. Graham Bruce from our School of Physics and Astronomy. This talk will last for about 30 minutes and then Dr. Bruce will be really happy to field your questions. We'll aim to wrap up the event by 6:15 at the latest, so do please get your questions in early during the talk if you'd like to ask anything. If you'd like to ask a question, then you can add that to the chat bar on your screen. Before we get into it though, I'd just like to do a quick plug for the next talks in the series. We still have 2 left in this calendar year, and the next one will be presented by Stephen Stewart, who has the huge task of being in charge of Saints Sport. That one will take place on Wednesday, the 26th of November. Then on Thursday, the 6th of December, we have the rescheduled talk by Dr. Maggie Ellis, who researches communication in all stages of dementia within our School of Psychology and Neuroscience. You can also access the full archive of all of our past Saints Talks on a range of subjects from AI in the workplace to Caribbean theatre on our dedicated St Andrews Alumni YouTube channel. And that's where this talk will also be available over the coming days. Before that though, let's get back to this evening's topic at hand and tonight's guest. Dr. Graham Bruce is a senior researcher and laboratory manager in the Optical Manipulation Group at the University of St Andrews. Graham received both his undergraduate degree in physics and his PhD from St Andrews, and his main expertise is harnessing light for measurement applications. He's applied this to a variety of topics over 2 decades, including developing techniques for quantum technologies, investigations such as assessing the health of developing embryos, and applied spectroscopy projects including whisky authentication and detecting toxic pigments in old books. His work has been recognised by major awards, including STEM for Britain and Museums and Heritage Awards. So without further ado, I'll hand you over to Graham for this evening's talk. Graham.
Thanks very much, Craig. Yeah, okay, so here is my talk this evening, and the title of my talk is Drink, Drugs and Toxic Books, Recent Adventures in Spectroscopic Sensing. I imagine that most of the people watching the talk understand most of the words in the title, but the word spectroscopic might be the one that's most likely to cause some confusion. So I'm going to start with a very brief introduction to spectroscopy. Imagine I've got some sample. I don't know what it is, and I want to find out what it is. Spectroscopy is the science of shining light at that sample and looking at the different colors of light that are emitted by the sample and using that to assess what is the makeup of that sample. So you'll see a few graphs in this presentation tonight. The graphs are all basically the same style of graph, where along the horizontal axis, we have a measure of the color of the light that's coming off of our sample. And the vertical axis tells us the brightness or how much light there is at each of those colors. So in this graph here, you can see, for example, we would be looking at a sample which emits 2 different colors, one slightly more strongly than the other. Okay, so here's the scenario. This poor student's been found in the university library, keeled over the desk. He's not very well, and we'd like to know what it is that's made this poor student unwell. And there's 3 candidates in this image. The first is this half-drunk bottle of booze on the desk in front of him. The second, there's a mysterious white tub with something inside it that we don't know what it is. And the third is this massive pile of books that's sitting next to him. And with the techniques that we've been developing in our research group, we're able to look at all 3 of those and tell you what is safe and what is not safe. So I'm going to start with the bottle of booze. One of the major projects we've been working on in recent years is looking at using light to authenticate whisky and other alcoholic beverages. So whisky's big business in Scotland, very important to the national economy. It actually is the 2nd largest industry in terms of Scotland's exports. So you can see that the only industry that brings in more money for the Scottish economy is oil and gas. And like any big industry, this becomes a target for counterfeiters. So there are estimates out there that around £200 million is lost every year to UK businesses due to the presence of these counterfeit alcohols. And across Europe, there's 1.2 billion euros lost every year in government taxation revenue. It's not just financial, though. There's also problems for health with low quality counterfeit alcohol. So 25% of the world's alcoholic drinks are believed to be illicit. And as I'm sure you've seen in the news recently, fairly regularly we see cases where people are poisoned by low quality alcohol. For example, the methanol poisonings that occurred in Laos around about Christmas time. So what we're going to do is we're going to use lasers to look at samples of whiskey and tell you whether they're genuine or whether they're fake. So first we need to know what is whiskey. Whiskey's a relatively complex mixture of molecules. We have water being the biggest component, 60%. The next biggest is ethanol at 40%. And then we have small levels of methanol, which is the one that's toxic that you definitely don't want, but it is always there in low concentrations, and other trace molecules that make up the color and the flavor and all the interesting properties of whiskey other than its alcohol content. And the goal that we set ourselves is, can we detect the different molecules and detect the quantities that those molecules are present in your whiskey? So although we draw the molecules as being those little static objects, molecules are constantly vibrating. And the technique that we use to do this involves basically shining our laser at the molecules that are in our liquid. And when the light interacts with the molecule can change the properties of the light. So often, actually, it doesn't change the properties of the light, that the light comes out at the same color as it went in. But this vibration and the interaction of this vibration with the light can cause light to come out either shifted to the blue part of the spectrum or shifted to the red part of the spectrum. And these changes are going to be the things that we're going to be looking for. So here's the sort of graph that we look at. As I said before, horizontal axis tells us about the color of the light. The vertical axis tells us about the amount of the light. So we get quite a lot of light that's going to come out unchanged. And then we're going to see these little additional colors that are being emitted by the sample, where some are going to be more blue and some are going to be more red. And each of these little peaks corresponds to a different sort of vibration in a different molecule within the sample. It's not important that you understand the details of this curve. What is important is basically what we're looking at now is equivalent of a fingerprint of the sample. So we can decode the information from this fingerprint that tells us what is the chemical composition of the sample that we're currently shining our laser at. We've been doing this for a number of years now. 2013, we were actually invited on to Dara O'Brien Science Club on BBC Two. I have a short clip to show you here of how well our method worked at identifying the whiskies. So what I'm going to show is a short video. I apologize if the quality is not particularly high, but the organizer is going to share a YouTube link with you at the end if you need to watch it again. So in this video, you're going to see two people. Dara O'Brien is the host of the show, and this gentleman here was his assistant. So we took our device down to the studios of the BBC, and we trained him how to use it in about 10 minutes. And what he's going to do now is he's going to challenge Dara to a taste test, where he's going to take a sample of whiskey, put it into our machine, and tell him what the brand of the whiskey is. And Dara's going to take a blind test, and then we're going to reveal whether he's right or whether. And we can do it in a relatively uncontrolled environment. This TV studio was obviously very bright lights, very warm, all these enthusiastic young people milling around.
I'm going to take the sample.
Now, the big challenge that we face is not being able to take a sample of the whiskey and authenticate what it is, but in general, with a high-value product like an old bottle of whiskey, you don't actually want to open the bottle, because opening the bottle destroys the value and the integrity of the whiskey. So we have had this challenge for a number of years now that we've been trying to solve, which is, without opening the bottle, can we just shine light through the glass, and can we tell if it's real or if it's fake? And the conventional way we would do this would be that we would take our laser beam and we would focus it down into the sample, and we'd measure the colors of light that come back out. And when we do that, unfortunately, what we find is that the alcohol content, the ethanol of the whiskey, gives us an absolutely tiny signal, and that the glass of the bottle actually completely swamps the signal that we're looking for. So we needed to come up with an intelligent way of bypassing the glass and not receiving any signal coming back from the glass. And the way that we've done this is that we've used methods of reshaping the laser beam. So rather than having just a laser beam that you might picture from your sort of sci-fi representations of laser beams, what we do is we shine our laser beam first through this cone of glass. This cone is called an axicon. And what that axicon does is that very close to the tip of the glass, we have all the laser beams crossing one another, and we get very bright pattern that looks a bit like a bullseye here. But as that light moves farther away from the cone of glass, it forms this nice empty ring. And so what we do is we use optics to basically produce this ring on the surface of the bottle here. And we have this nice bullseye pattern focusing the light down inside the bottle. And what we do then is that rather than collecting the signal that interacts with the glass and with the contents inside the bottle, we only collect light that comes back through that dark hole in the middle of the ring. Therefore, our device doesn't see any light that interacted with the glass. It only sees the light that came back from inside, and we get rid of all that annoying interfering glass signal. So here's an animation showing what happens to our spectrum that we measure. As we make the hole bigger, you can see that this glass peak falls away completely, and we're left with the underlying spectrum that allows us to fingerprint the alcohol inside the closed bottle. So here's a picture of how that looks in practice. Here's our bottle of whiskey, and you can see this ring of laser light shining on the bottle, focusing down inside. And what we're going to do is we're going to collect the light that comes back through that dark hole in the middle. And this works very well. This graph here, you can see that along the vertical axis, we've got different whiskies that we knew what they were, and we put them into our instrument and asked them to tell us what it thought they were. And you can see that on the diagonal of this array here, you can see that we've got for 9 times out of 10, when we gave it one of these Kleinlich 14 whiskies, it identified it correctly. And for most of the others, it was able to identify them correctly every time. Importantly, when we gave it 2 different bottles of the same product, it's also able to identify that these are the same rather than different. It's not just whiskey that we can use this for. We can also use it for other spirits as well. Here's cognac as an example. So cognac tends to come in 3 sort of qualities. There's the very special, I can never remember what the OP stands for, and the extremely old. And these are basically aged for 2 years, 4 years, and 10 years. And there's a massive price difference as you work your way through. And we can correctly identify what's the quality every time. In particular, one of the tests that we did to really prove that our method's able to look through the bottle and not be affected by the bottle was that we took some of the cheapest of the cognacs and we put them in more expensive bottles, and every time it's able to correctly identify what flavor or what quality of cognac was it that we were actually measuring. We can look for other specific things as well. So in this image here, you see we've got 9 bottles. One of these is a genuine whiskey. The other 8 are adulterated samples that are made to look like that whiskey. So on the left, what we've got is a cheaper whiskey with some caramel added to it to match the color of the original malt. And on the right-hand side, what we have is vodkas that are also artificially colored to look like the whiskey. And again, our method's able to detect what is the caramel. These bottles each have a different type of caramel in them to do this color matching. We're able to pick out what is the caramel that's in there. And that's very important because within the whiskey industry, there's only one caramel that's actually allowed to be added to product for color consistency reasons. And so we're able to detect that one or any of the others. So these cheaper caramels that counterfeiters might be using are easy to pick up. As I mentioned at the start, methanol poisoning is a big issue. This graph here shows what we can do. So along the vertical columns here, we actually have the spirit category. So we've identified whether we have a vodka, a whiskey, or a rum. And along the along the vertical, we've also been able to identify what is the quantity of methanol that's inside that drink. So if there was 9% methanol, that's a highly toxic drink. 2% is around about the guideline upper limit for human safe consumption, and we can identify lower concentrations as well. Now, moving beyond whiskey, it doesn't really surprise you that I can get my laser beam to go through the glass bottle and interrogate what's on the inside. But what we've been doing more recently is looking at increasingly challenging containers. So this is a white plastic pill bottle, the sort of thing that you might get from the NHS with your pills in it. And what we've shown is that we can also get our laser beam to go through the pill bottle and tell us what medicine is inside. So on the bottom here, you can see that we've got 3 different spectra, the blue one, the red one, and the black one, where each of these corresponds to a slightly different paracetamol product. The red one is pure paracetamol, the blue one is paracetamol with a little bit of added caffeine, and you can see that in the spectrum there's a small difference here between the red and the blue one, where we get this little additional peak. Then the black one is paracetamol with caffeine and aspirin, and again, you can see that this has got a slightly different spectrum. For example, we've got this additional peak here. Now, these are when we interrogate the pills when they're not inside any container. If you do a conventional spectroscopy and try and look through that barrier, what you see is that the spectra all look the same because all you detect is the spectrum that corresponds to the plastic of the container. But with our method, what we're able to do is we're able to reduce that signal that comes from the container down to a level that's sort of the same as the signal that you get from the pills that are in the inside. So we can look, for example, at these additional peaks that I was pointing out. You can see these in the spectrum quite clearly. So we're able to authenticate medicine inside the bottle. That's particularly relevant in lower resource settings, and I'll come back to that in a second. But at that time, my son was about 8 years old, and I was talking to him about what we were doing at work, about shining light through plastic, and he asked me, can you get the light to go through Lego? So we brought him into the lab with his Lego car, and we hid a paracetamol tablet inside the car, shone the laser beam through the roof of the car, and sure enough, we were able to measure the paracetamol inside the car. So good news, everybody, Lego criminals will now be caught. Okay, so I mentioned low resource settings. Where we're going in the next year or so is that we are going to develop an instrument that allows us to authenticate pharma medicines inside packaging. And particularly, we're going to deploy this in Ghana. About 10.5% of medicines in low and middle income countries are known to be substandard or falsified. And in West Africa, unfortunately, this can be as high as 80% by some estimates. Around about 120,000 children under the age of 5 die annually in sub-Saharan Africa due to substandard anti-malarial drugs. These are drugs that are shipped into the country claiming to be a certain strength and unfortunately are much lower strength. And this industry of providing illicit pharmaceuticals is generating massive profits for organized crime gangs. Now, one of the postdocs I work with, George, this is George in the yellow polo shirt here, is Ghanaian, and he brought this problem to us as a problem that we should get involved in. So what we're committed to do now is we're going to build a probe that we're going to take to Ghana. We're going to train local researchers in its use and its maintenance, and we're going to deploy that within the supply chain of the Ghana pharma industry in collaboration with Oson's chemists, who are one of the distributors there, and the University of Ghana, where we have local experts in pharmacy and pharmacology, and the optics experts in the Ghana Photonics and Optics Laboratory at the Kwame Nkrumah University of Science and Technology. So we're very excited about that. I'm sure in a couple of years' time we'll be able to share much more detail on that. But for now, that's what's coming in the near future with our through packaging chemical sensing. I'm now going to change gears slightly and talk about a completely different type of spectroscopy. So far, what we've been trying to do is get light through a barrier and measure what was behind the barrier without being confused by the chemical signature of that barrier itself. This second project I'm going to talk about is completely different. We were approached by university libraries and museums, in particular Pilar Gill and Erica Kotze there, who have been looking at the prevalence of arsenical pigments within Victorian books. So on the slide, you can see these 10 books from the Victorian era, different shades of green. And what they all have in common is that the green pigment that's in the book cover contains copper acetoarsenite, or more particularly within that molecule, we have arsenic. Okay, these books can have very toxic levels of arsenic within them. And they'd approached us to say, we've seen the work you've been doing with whisky. Is it possible to develop a similar instrument that will allow us to detect the presence of this arsenic in the cover of the books? So we estimate around 10% of the green books from the 19th century contain this arsenical pigment. One of the first clues that you've got a book that has this pigment is that unfortunately it's become more friable than other contemporary pigments in the time period. So if you pick up one of these books, there is a chance that you're going to be left with a green residue on your fingers, which clearly when that residue is made up of particles that contain arsenic, you definitely don't want to be licking your fingers when you turn the pages of the book. On the slide here, you can see two rows where we've taken little snippets of book covers. On one of these rows, all the books contain that arsenical pigment. On the other row, we have books that do not contain that pigment, but you can see that the colors are very similar. In fact, it turns out that the toxic books are in the top row, the non-toxic books are in the bottom row. But you can see that by eye, it's a very difficult challenge to actually identify which books are toxic and which are not. At the moment, there are really two main ways of detecting these books within a collection. The first is that the Winterthur collection at the University of Delaware have produced this kind of color matching bookmark, which gives you an indication of books that you should be concerned about, but it's going to vastly overestimate the prevalence of toxic books by doing this color matching, because really the human eye is not particularly well tuned to picking up these subtle differences in color. The other way that you can do this is by very expensive chemical testing, such as using X-ray fluorescence or spectroscopy in the same way that we were doing for the whisky and so on. But those instruments tend to come in a price point that's around about £10,000 or more. And they need trained operators, and they take a significant amount of time to perform the measurement. So the challenge that we set out to solve was, can you make an instrument which does not cost very much to produce, but can still detect these pigments in a reliable way? Just a bit of scale for the problem. Here's a few news clippings about the problem of these toxic books. So a piece in the Washington Post sort of outlining the fact that a lot of these books are in circulation. In 2022, 2024, some of these books were found, first of all, in a Leeds Council library and in the National Library of France. And what this has led is to a number of institutions basically removing from circulation all books of that time period that are green. So if you don't speak German, I'll translate the headline for you. This is from the University of Bielefeld in Germany, where they have isolated 60,000 books pending chemical testing because they don't know which books are safe and which are not. So two graphs on the slide here. The one on the left basically says if you only look at the visible part of the spectrum, the bit that we can see with our own eyes, it's very, very difficult to disentangle where on this graph do the points with red surroundings lie versus the points with black surroundings. So the ones with red surroundings are the books which are toxic. The ones with the black surrounds are the ones which are safe. So just using our eyes, you cannot reliably separate them out. What we've come up with is this approach where we look at specific parts of the spectrum, and we're able to basically split out most of the toxic books into this one region of this graph here, while most of the safe books sit in other quadrants. And we very deliberately drawn these lines in a regime where we catch all the books that are toxic. And okay, we have a few books that are sort of miscaptured as potentially being toxic, but importantly, we don't see any of these toxic books in any of the other regions. So here's a little pictographic history of the development of the instrument. We started off with this very warts and all physics department prototype, where you can see this bright light that we shine on the books, and we have a sensor next to the light that picks up the light that's reflected back from the book, and we pass it down the USB cable there to a computer to do the analysis. We moved on to something a little bit more sophisticated, where we had this little pod that you placed on top of the book, and it still was connected to a computer to do the analysis. And ultimately what we've come up with is this tool here, which is a little handheld gun-like tool. Looks a bit like a supermarket checkout gun or something like that, where you pull the trigger and it will go beep and show a green light if the book is safe, and it will go boop boop and show a red light if the book is dangerous. And we're able to do that in a really handheld, easy to interpret fashion. So what we've been doing in the last year is that we've been going around a number of collecting institutes across Scotland. So you can see here we've collaborated with National Trust for Scotland, the Abbotsford Trust, where we had access to the Library of Walter Scott, University of Edinburgh and Glasgow, Library of Innerpeffray, which is the oldest lending library in the world, as well as National Library of Scotland, National Records of Scotland, and a few local council libraries as well. in work that was funded by this Photonics and Quantum Accelerator. So these are the locations that we've been to test the books. You can see some of the social media posts that came from these collections. During these visits, we've inspected more than 11,000 books, of which we've been able to confirm that around about 160 actually had this particularly toxic pigment inside. So the project generated quite a bit of interest. We were highly commended, or in other words, we were the runner-up in the Museum and Heritage Awards for 2024 in the category of Conservation or Restoration Project of the Year. You can see the other key team members for this project here. Pilar Gill, who's a heritage scientist at Libraries and Museums. Erika Kotze, who's one of our conservators at the book, very on-brand handbag that she took with us there. And the postdoc that I had working on the project, Morgan Fakin. So, the future. Well, some of you have probably seen this already, but we appeared on BBC Scotland recently discussing this project. Here I am with the tool in hand, explaining to the reporter how this tool actually works. This has led to us being contacted by libraries and collecting institutes around the world, UK, North America, Australasia, South Africa, all across Europe. And we've now got actually fast approaching 120 requests for delivery of one of these tools. People want to actually use the tool. So we're hoping to have a production run somewhere between now and Easter, hopefully, so that we can start spreading these around the globe. So going back to where we started, this poor student who was slumped over the desk, was it the contents of the container? Was it the contents of the bottle? Or was it the pile of books? Well, I'm not going to answer the mystery for now, but safe to say we're actually able to answer it. So before I sign off, just to thank all the people that I've worked with on this project. We've collaborated between the University of St Andrews and the University of Adelaide and the Scotch Whisky Research Institute on the project of authenticating alcohol. Authenticating medicines is being done between here and our Ghanaian partners. And we've got we've been a collaboration between the School of Physics and Astronomy and libraries and museums. In particular, we've been ably assisted by Chris Booth, our electronics technician. And if you'd like to find out more, you can find out more on our group webpage or on the project webpage for the Poisonous Books project. And thank you very much for your attention.
Thanks very much, Graham. That's really fascinating. I can think of much worse ways to spend a Thursday night than with whiskey and old books. So it was a pleasure to listen to you. I think it's a really good example as well of how St Andrews departments and academic areas are working together across disciplines to really kind of tackle these problems that we see. And it's amazing to see St Andrews being a world leader especially in the books project as well. I know that's got applications kind of far beyond St Andrews, so it's really nice to see. Just a reminder to our watchers that we already have a number of questions in, but if you have questions to ask Dr. Bruce, then do please get them in the chat bar, and we'll ask as many of them as we can before we finish up. Just to kick off, though, I was going to ask a question about. It's obviously really amazing that you can look through the glass into a bottle of whiskey to do this this investigation. But it occurred to me, does the color of the glass matter? Because obviously there's a kind of a range of different colors of whiskey bottles, even a range of different greens in a whiskey bottle. So how do you tackle that and mitigate the effects of that?
Yeah, that's actually a fantastic question. So the colorless glass bottles were where we started, because obviously that's the low-hanging fruit. But actually, the research project that my PhD student Annie Kritzinger has been working on in the last year or so has been colored bottles. And we've now developed a variation of the methodology that you've seen here, where we are able to quickly change the wavelength of our laser. And by doing that, what we're able to do is we're able to disentangle any fluorescence effects that the bottle might produce from the behavior of the contents. So now we're able to look through bottles of all sorts of different colors, so greens, browns, blues even, for some of the gins and vodkas. They come in particularly interesting bottles. But that's a problem that we've solved very, very recently, actually. Yes.
I'm going to stick with a whiskey for the moment, because we've got a question from an anonymous viewer who's asked, where's this method of detecting counterfeit whiskey and other spirits being used currently? I don't know if you can speak about that in terms of commercial sensitivities, but if it's
Yeah,
being used in the wild, that would be great. I've actually got a little follow-up question of my own as well, which is,
yeah.
there's obviously thousands and millions of spirits out there. Where do you get your kind of database from so that you can figure out what something is?
Both very good questions, and actually the answer to both questions is the same. So our main partner at the moment is the Scotch Whisky Research Institute. They are the sort of research and development arm of major whisky producers in Scotland. So they sit separate to the individual companies. They're sort of co-funded by around about 18 different companies. And they are going to be taking delivery of an instrument from us very soon. And they will be basically testing that in their site, which is in Edinburgh, and they will be presenting it to the big whisky companies. We have a few other contracts that I'm not able to talk about, but in order to get the database of whiskies, we actually have been working with the companies and working with the Scotch Whisky Research Institute, who've been providing us with samples that we've been able to sort of build up a library. Long term, the way we kind of see this is that the people that want to use this, generally speaking, have a very specific question, which is what's in my bottle what it says on the label, right? And so that problem is a slightly narrower problem and a bit easier to tackle, because all we need to know is, well, what should it look like when it's in that bottle? It doesn't matter what it is if it's not the thing that it's supposed to be. Yeah.
A quick follow-up on the previous question as well. Someone has asked, Alistair Batty has asked if the varying thickness of the glass is something that you have to contend with when you're doing these measurements.
Yes, that's a good question as well. So the thickness variance between different bottles is not particularly problematic. It just causes the signal strength to go up and down. Some of the bottles have quite an uneven texture. And so at the moment, one of the sort of engineering challenges we've got is that it helps to be able to take the bottle at a particular orientation each time. It's not essential, but it definitely makes the measurement easier. But that's an engineering challenge that we're currently tackling as well.
I'm going to move on to the drugs research now. Ella Bryson has asked, how close does the probe need to be to the sample? And would it be possible to use this, for example, for screening luggage at airports for illicit drugs that are going through?
Yeah, two great questions. So at the moment, our instrument has a sort of operational distance on the order of a few centimeters, 5 centimeters or something like that. That's the way we've designed it, because that gives us the highest amount of signal strength. But there is research being done by other people, particularly in Sweden, where they've looked at making similar measurement techniques at a long distance. In particular, the application that they had in mind was looking for landmines and improvised explosive devices, looking inside packaging for that. So it's possible to do this at ranges of up to meters. It's not something that we've had to do at the moment. The airport scanners is something that we've been thinking about as well, that it definitely feels like there is applicability there. It's not something that we've started to do anything with, but it's definitely an interesting suggestion.
Thank you. Apart from kind of spirits and medicines, are there any other areas that you can see this application or this technology being applied in the future? Or are there other areas that you're working on?
There are other areas that we're working on that I'm not at liberty to discuss at the moment. One thing that I can say is that we've had a number of undergraduate project students working with the technology, one of whom was looking for explosive precursor molecules hidden inside plastic bottles. So that was actually the sort of airport security kind of question that we had in mind there. You can clearly detect explosives inside plastic containers, for example. We've also had project students looking at things like, can you use similar techniques to detect things like microplastics inside aquatic organisms, for example? which is very early stage, but the signs that we've got so far are that, yes, we can differentiate between the presence of natural matter and plastic matter inside the gut of small sort of aquatic organisms. Yeah, basically what I say to people when I'm giving technology demonstrations is that if you have an application in mind where you have some chemical that you want to assess and it's hidden behind a barrier, let me know, because I'd be interested in trying.
The call to action for everyone watching. I'll move on to books now. And I was going to ask, if I have one of these books or a green book that I think might be toxic, what should I do with it? What's my kind of first action in terms of making sure I'm not poisoning myself?
Yeah, so the first thing that you should do if you're suspicious about one of your books is you should get a Ziploc plastic bag, like the sort of thing that you might have sandwiches in, and put the book inside there and zip it up, and then wash your hands carefully. Once it's in the bag, it's not going to present any further threat to you. That's a precaution that just to make sure that you're not going to be continuing to be exposed to any particles that might be shed off the book cover. Realistically, we think that the risk with these books is not going to be the one-off interaction that you might have with a single book that you pick up in a used bookstore or something like this. We really think that the risk is higher for people that work in collecting institutes where, you know, there are going to be hundreds or potentially thousands of these books slowly shedding particles into the environment, and then somebody's getting microdosed over a long period of time. But yeah, if you've got one and you want to have it assessed and you're in the area around St Andrews, we're certainly happy to look at books that people might want to bring in. And hopefully, soon these tools are going to start making their way around the world and hopefully be available. So if you've got something that's causing you concern and you want our opinion on it, there is a facility on that Poisonous Books website that I put up earlier where people can report the books that they've got, and we're able to get back in touch with them and see what we can do to help.
Great, thanks. So I've worked a bit with the library on the kind of publicising this books project and the poisonous books. So I know there's a lot of interest from other areas as well, and it's has great kind of commercial application. Someone in the chat has asked what sort of cost the book tool will carry for interested parties. So I don't know if that's a point that you've got to in the process yet, or whether it is something that you intend to do.
That is something that we are currently trying to establish. The idea is that we want to set this at a price point that is accessible for all. So we're not planning on selling these at thousands of pounds or anything like that. The likelihood is we're going to be looking at something in the order of a couple of £100. But we're still sort of developing the business model for how we can sort of sustainably produce these. Watch this space. It should hopefully be something that we've arrived at by around about the spring.
Yeah, right. And somewhat related, Morris Bryson has asked in the chat. Well, firstly, thanks for the excellent presentation, he says, and then also the business applications are very clear for all of your lasers, and I guess it means all of the different applications that you have. And have you created a company to expand the work? And if so, what's the name? But I don't know if that's something, because we have various services around the university that will help for the commercialization of companies. So I wonder if that's something you could talk about and whether that's a road you intend to go down.
It's a road that we are thinking about going down in a couple of those directions that we've discussed. We haven't actively done that yet, but we are sort of making early steps of trying to identify freedom to operate and identify who would be appropriate partners, for example. But St Andrews Innovation is supporting us in that journey and trying to identify what's the correct route for the technology going forward. And I know that they've already done so with other members of our school, for example, in trying to spin out companies. So we're not there yet. That's something that we are contemplating, but no company name yet.
I look forward to that. I have an unusual anonymous question who's just asked, did you come across the changing shape of the light of changing the shape of the light to increase the speed and accuracy of paper tape readers for Colossus in 1944-45. That's quite niche, but I wonder if that's anything you've ever come across.
That's not something I've come across, but in general, that reshaping laser light has been kind of one of the themes of my career. That was something that I was doing when I was a PhD student. There's lots of different tricks and techniques and methods for reshaping laser light. The one that we come up with for the ring here is one that we spent far too long trying to come up with, and in the end, the solution was very simple. But yeah, there's lots of things out there. I'm not familiar with that particular work, but yeah, there's lots of things out there that harness this ability to reshape laser beams and then use them in interesting new ways.
I think this will probably be our final question, unless anyone is furiously typing at the moment. But and this probably goes into more economics than you're used to, but is it likely that your whisky detection techniques can now send the investment markets tumbling as investors' confidence becomes knocked?
I hope not. That's not our goal. So the goal is actually to provide assurance, right, for people that are investing in these things, rather than to cause any panic. Yeah.
And do you actually see much counterfeit whiskey in Scotland, or is this it's more across the world, or is that?
I think it has its impact on Scotland as well.
Yes.
Yeah. It is a global problem. It is more prevalent in other areas than it is in Scotland, but it is a problem in Scotland as well.
Okay. Right. Well, I think that's all we've got time for at the moment. But that was it. Just falls to me to thank Graham for a really fantastic talk. It's really interesting, and it's really great to get these insights into the kind of research and passions of our academics every couple of weeks. So so thanks profusely for taking the time to talk to us on a subject about which you're clearly passionate and world leading in. Thanks also to the staff who've given their time to make the arrangements for this event. And there's a lot of work that goes into these, and it's very much appreciated by all of us. And finally, a big thank you to you, our esteemed alumni, students, staff, and friends for attending the talk. We're delighted to be able to welcome you virtually back to St Andrews every few weeks, so please continue to attend these events. As I said, the next talk is date for your diaries on the 26th of November with Stephen Stewart talking about his role at Saints Sport. We look forward to seeing you then, but for now, thanks very much for joining us and enjoy the rest of your evening.
Thank you.